Okay, so last time we showed proposition 1.13. One point 13 claim the following equality. So if you have interval CD, you have interval AB. Between them, you have a phi. Phi is continuous, non-decreasing, and onto. Okay? And from AB, you have a gamma, continuous, rectifiable. From AB to C. And from C, you have continuous map defined at least over the image of gamma. F. Then you can define the integral from f along gamma over gamma along gamma, and this is like this, right? Or you can imagine that you can start from CD to the final stuff. F along gamma compose phi. And the proposition 1.13 claims these two quantities are equal. Okay, these two quantities are equal. Okay, so we basically use the definition and the uniform continuity stuff. Okay, so in the restriction of a phi, we only require non-decreasing. Non-decreasing is slightly weak because it could be like constant. Over certain interval, it could be constant. For example, it could map a small interval from C to certain moment, to certain point, constantly to A. If that happens, you cannot go back. Okay? So the next definition, we're going to define some equivalence relation. If you have some equivalence relation, you need to go forth and back. And then this non-decreasing condition is not enough. It should be stronger than non-decreasing. Okay, now let's see what is the definition. So let sigma from CD to C and gamma from AB to C be rectifiable path. Then we say sigma is equivalent to gamma. Sigma is equivalent to gamma if there is a function phi from CD to AB with which is not with, which is continuous. So you see, that's first condition. And stronger than non-decreasing, I want to avoid this constant situation, then it's strictly increasing. Strictly increasing, it means there's no constant subinterval. And onto. Okay, onto. Onto basically means it will map C to A and D to B because of this strictly increasing condition. Strictly increasing condition. Okay? Okay, if such phi exists between CD and AB, then we say those two paths, sigma and gamma equivalent. And okay, such onto with the additional another condition such that sigma is gamma compose phi. Now we're not done. Sigma is gamma compose phi, and we call the function phi a change of variable. Parameter variable. Change of parameter. Okay, so let's see what we have. We have CD. We have AB. We have this complex plane. Then from CD we have sigma. From AB we have gamma. Then if such phi exists, with this condition, sigma is gamma compose phi. Technically, you have the same image set. This condition gave us the same image set. And we say this diagram commute. Okay? It's equivalent. It is equivalent relation. It means sigma is equivalent to gamma and gamma is equivalent to sigma. Then if phi exists, then phi inverse also exists, right? It's a phi inverse. Phi is strictly increasing. It guarantees that phi inverse exists. And phi is strictly increasing. Phi inverse is also strictly increasing. Phi is onto, then phi inverse is also onto. Phi is continuous. Phi inverse is also continuous. So that guarantees the equivalence relation. And they share the same path. Basically, you can realize this path by this gamma, or you can also realize this path by this sigma. So between gamma and sigma, you can change the parameter. So that's why this function phi is called a change of parameter. Okay, so this path does not, of course, it depends on the realization of a gamma and a sigma. It has several equivalent realization. So this is called a curve. So you see, well, up to here, this end of the definition. Then you say a curve is an equivalent class of path. Okay, so curve, this set is actually an equivalent class of the path, equivalence class of realization. For a curve, you have a lot of realizations. And for the curve, we say the curve is smooth. A curve is smooth or piecewise smooth. If and only if one of its realization or representation is smooth. Okay? So basically what it means, for example, if you drive from San Juan to Mayagüez, you have a smooth curve, a smooth path, or smooth highway. But during your drive, you can stop at a certain moment, or you can get a sharp break, a sharp stop, and then you get a fast movement, and then you get a slow movement. But these actions will change your velocity dramatically. It make your velocity not continuous, right? You stop, you fast increase, you get a high speed, not high, high velocity, and then you stop and you get faster speed, for certain reason. But those actions actually do not change the property of this curve. It just change your realization. You could also just smoothly drive from San Juan to Mayagüez. Okay, so that action is actually a smooth action. that realization is smooth. If that realization is smooth, it guarantees that this set is actually smooth enough. So we say a curve is smooth is a one of a realization is smooth, okay, or piecewise smooth. Okay, so now let's focus on the curves. Whenever we have a curve, we actually have a realization already, at least in your mind. Okay, when you talk about the curve, you're talking about one of the realization. Of course, we will also choose a good one, a smooth one, if possible. Okay, so next, let's manipulate this path. So let gamma from AB to C be a rectifiable path. Gamma is a rectifiable path. So gamma A, gamma B. Okay, then you start from gamma A and you're going to move along this gamma. For example, when you have T here, when you move gamma from A to T, gamma T, then it is this point, gamma of T is on the curve or on the path, whatever. Then from gamma A to gamma T, there is a curve we compute. The length, we compute the length along the curve, arc length, and we call it absolute value of gamma evaluated at T. Okay, so what is the absolute value of gamma evaluated at T? It is the supremum, which is the total variation of sigma k from 1 to n, absolute value of gamma tk minus gamma tk minus 1, where this T0 and Tn is a partition of the interval a t. Is actually the total variation along the subinterval. Okay, so it's like the total variation of a gamma over the interval a t. Okay, so this absolute value of gamma is the measurement of the partial arc length counting from the gamma A. So absolute value of gamma, it has a domain AB. It's mapped to the real numbers, and actually it is mapped into 0. What is 0? Gamma, absolute value of gamma of A is 0 to the total variation of gamma along AB. It's a closed interval. It's a closed interval. Okay, and also because you always move it, it's increasing. So gamma is strictly increasing. Strictly increasing. Well, it's not strictly. If gamma, this original gamma is the original gamma is a constant function. Of course, it's not increasing. My bad. It's not strictly increasing. It's just non-decreasing. It's increasing. Okay, and because you have a monotone function, we clearly know that this absolute value of gamma is of bounded variation. it is of bounded variation. Okay, so once you have a bounded variation function, so we can define what? We define the f along the absolute value of dz, absolute value of dz along gamma. It is, by definition, this is definition, is integral from a to b f of gamma of t d absolute value of gamma t. Okay, this is a new definition. It is a new definition. Remember, f d gamma, f dz, my bad, f dz is from a to b f gamma t d gamma t. Okay, so here there's no ops value. If you put ops value, you're going to use this ops value of gamma. They're different. They are different. Okay, so we define our second integral, a special one. Another thing, we said we start from gamma A and we move to gamma B. Of course, you can start from gamma B and move back to gamma A. Okay, so we define negative gamma of t, the negative gamma of t, to be gamma of negative t for t belong to negative b and negative a, negative b to negative a. All right, so what does how do we get it? For example, you see the gamma of negative b, negative gamma of negative b, because it starts from negative b. By definition, it is gamma of b. So this is the initial point. And when you have a negative gamma of a, this is one function. This is a new, be careful, this is a new path. It's not a negative of gamma a. It's not this one. It's you have to understand it like a negative gamma and then evaluate at a, not negative of gamma of a. That's different. Okay, so negative gamma evaluated at negative a is gamma of negative a is gamma a. This is terminal point. And when you move from negative b to negative a, you do move from gamma b along the curve to gamma a. So this is a go backward. So that's why we call it a negative. You change the direction, you only change the direction, you do not change any other point. So sometimes, we say sometimes, we denote gamma to the negative 1 to be negative gamma. Okay, so we use this one if we want to use a multiplication group. We use this if we want to use a additive group. If we want to have additive group, either way, it's just the inverse, the opposite direction. Okay, good. And another one is a translation. So you have this curve, you just move it to a different. Like for example, you move it vertically down, or you move it horizontally to the right. Either way, so the translation for a number c in C, let gamma of C evaluated at t to be gamma t plus c for t in AB. You see, here there's a small difference. If you want to get the inverse, the negative or inverse, you actually change the domain. Domain becomes negative b to negative a because you are going to put a negative sign. But if you get a translation, you share the same domain. Gamma t is between a and b. Okay, you do share the the same domain in this moment. Okay, so that's the translation. With inverse, absolute value, and translation, we have the simple proposition 1.17. The proposition says, let gamma be a rectifiable curve and suppose that f is a function continuous on the trace of gamma, and the trace of gamma is continuous, then we have a, the integral f along gamma is equal to negative f along negative gamma. So this one looks strange, but actually you can write it this way: f integral f along gamma is equal to along negative gamma is equal to negative integral of f along gamma. Just move this negative sign to the other side. So now it looks better. You can move this negative sign to the front. And also we understand that you change the direction of the curve. So you change the direction of the curve, you get a negative sign. Okay, you change the direction of a curve, you create a negative sign. This creation comes from this sigma f gamma tau k. This part does not change, k from 1 to n. The change is gamma tk minus gamma tk minus 1. This part, when you change the direction, you will create a negative sign. You go this way, you have here, this is the initial point minus subtract the terminal point. If you go the opposite way, you will create a negative sign. That's a places. That is place you have a negative sign. Okay? Change the direction, get a negative sign. And second, B, absolute value of f along gamma is going to be bounded by the integral of absolute value of f dz absolute value along gamma. Okay, like you pass this integral into the you pass this absolute value into the integral, you get this. And of course you have to understand what is the absolute value of dz mean. This just means remember, this is integral of f a to b and d gamma absolute value of gamma of t. This is evaluated at the gamma of t. Okay, the evaluation at the gamma of t. This, if you want, you can put the more complete version. But to emphasize this part, we need this. Okay, and this one is less than or equal to the total variation times the supremum of the absolute value of f of z. Z belong to the trace of gamma. Well, this one is obvious because when you replace this quantity by the supremum, and then this integral is just the total variation of gamma. Okay? C, we have, if we have a translation, if point C belong to it, then we have a translation. Remember, the integral f of z along gamma plus c dz is equal to is equal to this. Okay? In the book, it's written like f of z minus c dz. No, 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 no. The book is the right one. This is not right. Okay. F z dz. F z dz. Yes, f z dz. The thing is the following. You see gamma plus c, you originally has a gamma. And you shift it to, by c, you shift it to this place. This is gamma plus c. But the original f is defined only on gamma. So when you have gamma plus c, you have to use z minus c to move it back. You use z minus c to move it back and to get a gamma, and then you evaluate f along gamma. Okay? And with this move forth and back, this action, it does not change the integral. The origin, my understanding, is not necessary. Well, what I try to understand is the following. If f is both defined over gamma and gamma plus c, okay? If it is defined over gamma plus c like this, what I'm trying to explain or modify is like this. You can add this c if, for example, if f is defined over gamma plus c, this trace, you can add this c, this is gamma, along the curve, or you can add c directly to the variable. It's the same action. It's the same action, but here it means you go, you translate forward and backward. It's the same thing. Okay, so in principle they mean the same idea, but the difference is that here f is defined on the trace of gamma. This place f is defined on the trace of gamma plus c. So they have slightly different definition, meaning. Okay, so here you actually have f on this part. Here you have f on this part. With this one, f is also defined over gamma plus c. Here f is defined over gamma plus c. Same thing. All right. Okay, so the proof is you are going to try to prove them all these stuffs, and the proof will basically depend on the definition of a Riemann-Stieltjes integral. First one is exactly the Riemann-Stieltjes integral. You try to write this in the sigma Riemann-Stieltjes sum, and you will see the negative sign. The negative sign comes from the subtraction. The negative sign will come from the subtraction. And second one, you also have this, you need some triangle inequality. The third one is exactly the same thing. You just do the addition subtraction. Okay? Okay, so the next theorem, we're not going to prove it in this part of the video, but we will continue the lecture on this topic. Okay. The next part is the theorem 1.18. It's a fundamental theorem of calculus, but in the complex analysis for the line integral, it says let G be open in C. G is an open set in C, and let gamma be a rectifiable path in G. Rectifiable is used when we can define this Riemann-Stieltjes integral with initial and endpoint alpha and beta. Okay, like this is like the gamma A, this is the gamma B, alpha and beta respectively. Okay, and one more condition. If this continuous function f from G to C is a continuous function with a primitive, with an antiderivative, with a primitive capital F from G to C. Okay, then what we can say is that this integral f along gamma is equal to capital F of beta minus capital F of alpha. Okay, so here the author explained the relation. What is a word? What does this word primitive means? Primitive just means capital F prime is equal to little f. Okay, so this condition is very, very, very strong. Why? So for example, you have this open set G here, and you have a map F from G to complex plane. And we have initial and term endpoint gamma, beta, alpha, beta. And then we have a primitive capital F. Then basically it says you get integral either this way or this way or whatever way. I don't care what is the connection between alpha and beta. Once this path is rectifiable, this integral is always capital F beta minus capital F of alpha. So here the integral is path independent. The path independent. So that is a very, very strong result. That is a very, very strong result. Okay? The thing is that it's slightly different from the fundamental theorem calculus in the calculus. In the calculus, we only have one line. Then we have integral from a to b f prime of x dx is fb minus fa. This is our FTC, fundamental theorem of calculus. But in this situation, what do you see? We have the standard one from a to b, the integral. Or we can go to the left and go to the right further and come back. But the thing is that if you go back and forth, this part, they are cancelled. Here you go further and back, this part they are cancelled. So you actually only count this. Other parts are cancelled. Okay? So only interval AB gives the integral value. Other parts are cancelled. The thing is that in this complex world, there's no part cancelled. Okay, so you see, you choose this gamma, assuming it's rectifiable, or you choose different gamma. They don't even share any common part. I mean, except the point. They don't even share the common part. I mean, we can get this. We can get even smaller one. There's no shared part. Or we get this corner. So if they don't share the part, how can you imagine they cancel something? So there's no cancellation. No cancellation, it makes the complex world more different than the real line. Okay, so that's the big difference between the complex analysis and the real analysis. Real integration. The complex integration is more complex than this one. This one, even though we also know that it is so-called the path independent, but this path independent actually come from the cancellation, or you can understand it from the cancellation. But the complex analysis, you cannot understand it from cancellation. It's a pure property. But so far, we do need to assume it has a primitive, a continuous function with a primitive. All right. Okay. We finished this video at this point. We're going to start prove the theorem 1.18 by proving one lemma first, 1.19 first. Okay. We'll stop the video at this moment, and we'll continue lecture in the next video. Thank you.